All right, hello everybody. Here we are again, another great video. Awesome learning of math we're about to do. So first of all, I've got this meme that I found here that I thought you guys would really enjoy and probably relate with right now. As well, for any of you that have had me in the past, you know that I have a policy where I usually ask for at least 3 decimal places in any answer, so perhaps you relate with this meme with some of my grading. Okay, so we are working on section 1.3 now, so just continuing the review of some stuff from Precalculus. And the first thing we have to look at here is transformations of functions. So looking at when we do transformations of a standard function, how the formula changes based on the different transformations that we have. So here we have the graph of the function y equals x to the 5th. It's shifted left by 3, up by 10, and then stretched vertically by a factor of 2, and they want us to write a formula for the new function. So first thing we want to do is identify the different transformations we have here. So we have first of all, the left by 3, the up by 10, and then stretched vertically by a factor of 2, and that term vertically is something we need to pay attention to because that will tell us where in our formula the 2 is going to go. All right, as we do this, we also have to think about inside and outside transformations. Remember, inside transformations, those are the ones that impact the inputs of a function. Outside transformations, those are the ones that impact the output of a function. Okay, so I'm going to start by dealing with that that transformation that shifts the function left by 3. So this is a horizontal movement, which means I'm moving along the horizontal axis, which I know that the inputs are along the horizontal axis, so this is going to be an inside transformation. And so I'm going to call my new function here, I'm going to call it g of x. And because I'm being shifted left by 3, I know that's going to go inside the function, so it's going to go in where the x is here, inside the function. Also, if you recall, we have a nickname that I've used in my classes for the inside of the function, and we call that the house of lies. And we call it that because it does the opposite of what we think it would do. So here, we're moving left by 3. So if you think about a coordinate axis, like that, if we're moving left by 3, we're going this way. And we know that usually more negative values are there, so we'd expect there to be some sort of a subtraction by 3 here, but because it's the house of lies, it's actually going to do the opposite, and so it's going to add 3. So on the inside here, we're going to have x plus 3. Okay, and that's now raised to the 5th power. So that is how we deal with that. Okay, so it goes on the inside and it adds instead of subtracting. All right, next we're going to look at what happens when we shift up by 10. So that's shifting up and down on the vertical axis. So that impacts outputs, which means this is going to be on the outside of the function. So how that's going to change here is we're going to have g of x equals, we have x plus 3 raised to the 5th. And then because we're going up by 10, that happens on the outside, we're going to add 10 on the outside of our function here. Something like this, g of x equals x plus 3 to the 5th plus 10. And let me go ahead on my problem up here, mark what order I'm doing these in. So we did this one here first, this one here second, and now we're going to deal with the stretching vertically by a factor of 2 third. Okay, and so if we're stretching vertically, that means we're stretching up and down. So that's another outside transformation, which means it's going to impact the outputs. So this needs to be on the outside of the function. And if we're stretching vertically by a factor of 2, in this case, because it's outside, it's not the house of lies, it does exactly what we think it should do, so it'll multiply our original function by 2. So we should have then g of x equals 2 times x plus 3 to the 5th plus 10. And that would be our answer here. So that's what we're looking for. So again, just to reiterate what each thing means here. So the 2, that's our stretch vertically by a factor of 2. The plus 3, it's on the inside, it's in the house of lies, so it does the opposite of what we think, so it moves to the left 3. The plus 10 here on the outside does exactly what we think it should do, so it moves the function up 10 units. All right, let's move on. So now we're looking at composition of functions. Remember, composition of functions is when we're putting functions within functions. So it's kind of like our Inception, if you remember that movie, Inception with functions. And remember, when we do composition of functions, we always start on the inside. So here, looking at this first one, the f, whoops, sorry about that. The f of g of 3. So we're going to start on the inside of this function. So with the g of 3. So the first thing we need to do is figure out what g of 3 means. If you recall from earlier PowerPoints, g of 3 means take 3, put it as the input for g of x. So do a little scratch work here off to the side. So g of 3 equals 3 plus 1. So that will give us 4. And so that's the output when we have g of 3, but that output now becomes the input for f. So we're going to take this, we're going to put it in the place here of where we have the g of 3. So what we end up with here is f of g of 3 now is going to equal f of, on the inside now we have 4. So that's our input now for f. Okay, which means now again we use that as the input value in f, so we'll do a little scratch work over here. So we'll have f of 4 equals square root of 4, which we know is 2. So then we have here that f of 4 is 2. Okay, sorry for that terrible 2. So that's the first one. So the f of g of 3 is equal to 2. All right, I'm going to clear my drawings here, and now let's look at this next one, the f of g of x. Now notice what is different here is that this time they have not given us a value for x. So we just have f of g of x, but we can still deal with this the same way we dealt with the last one. Okay, so by starting on the inside, so we start here with this g of x. And again, there's nothing to input into g of x there, so we're actually just going to take the function g of x and plug it in to the function f. So what this will look like, so that f of, instead of g of x, we'll put in what the formula is for g of x, which is x plus 1. Okay, and that x plus 1 now, that'll be the input for the function f. So that'll go in the place of wherever the variables are in f. So this would become square root of the thing that I underlined, which is the x plus 1. Okay, and so now just write a final answer here. We have f of x equals what we get when I put those two functions together. Now you'll notice the second direction here says define as domain. I'm not going to go over that right now because we did that on a previous video. So you may want to refer back to that. I believe it's the first video for section 1.1 and 1.2 has the information for that. All right, and then looking at the last one here, we're asked to find now g of f of 3z. So notice on this one now, we're doing composition of functions. F is on the inside this time, and now we have this 3z that is here inside of the function f. Now, even though that contains both a number and a variable, we can still deal with it the same way we deal with numbers in that spot. So we'll do a little scratch work off to the side. So f of 3z means take 3z and plug it into the function f. This will become our input. So we'll have square root of 3z. And so that's what f of 3z is. So now that, I'm going to box this in green. Since f of 3z equals this now takes the place of f of 3z over here. So we'll have now g of, whoops, sorry about that. No, g of square root of 3z, that's our input now. Okay, and this will become, that's going to go in the place of the variable in the function g. So this will become square root of 3z, that value plus 1. That will be our final answer there. There we go. So that's a little bit about composition of functions. I know this can often be a tough subject for students. So if you have any questions on that, please let me know. All right, now the next thing is inverse functions. So before we start to solve this function, they ask us to find the formula for the inverse function below. Should first remind ourselves, what is an inverse function? Remember, an inverse function is a function that switches the inputs and outputs of a particular function. And yeah, so here, first thing we probably want to do is identify what our inputs and outputs are. And we see that we have the function is called, whoops, excuse me again. The function is called f of x, so it looks like x here. That will be our input, and then f out here, that's the output. Okay, and so to find the formula for the inverse, first thing I'm going to do here is rewrite this in a little simpler form. Do it here off to the side and left. So I'm going to write this as f equals 7 over x plus 1. And then as I mentioned, an inverse function switches the inputs and outputs. So what I need to do here is switch, since x is my input and f is my output, is I'm going to switch the f and the x, have them switch places. Okay, so what we get when we do that then is x equals 7 over f plus 1. We know generally when we do this, usually x is our input variable and f is our output variable. So what I need to do now is solve for f. So I need to isolate this f. So to do that, the first thing I'm going to do, well, I notice that this f plus 1 is down here in the denominator, and I would like to get it out of the denominator to be able to deal with it. So to do that, I'm actually going to multiply by, do that, f plus 1 on both sides of the equation. Multiply it by it here, multiply by it on the left-hand side. Okay, And so what we end up with after that is x times f plus 1 equals, over on the right hand side, we have f plus 1 in the denominator, f plus 1 up here, so those two can cancel out. So we'll just have equals 7. And then before I continue on, I'll want to distribute that x that is outside the parentheses here. So distribute to the f and to the 1. So what we get next then is xf plus x equals 7. And again, we're trying to isolate the f. Yeah, so isolate this. So we need to do something with the two x's. So the first thing I'll do with the x that is the plus x, I'll subtract that from both sides. So subtract x here, subtract x here. So then I get x, maybe x xf equals, and then we cannot combine the 7 and the x, they're not like terms, so that's 7 minus x. And then to isolate, or to finish to isolate the f, we'll divide by the x here because it's being multiplied. Divide the whole thing on the right hand side by x. X is on the left hand side, cancel. And so what we end up with is f equals 7 minus x over x. And now we found a formula for the inverse. Now, very quickly, before we write our final answer, one thing I know some of us might be tempted to do is to try to cancel out these x's here. But we cannot do that because they're being divided, and also the x on the top is being subtracted from the 7, so that's not allowed. So this gives us our final formula. One more thing we have to do to write our final answer is, because this is the inverse, if you recall, we have that special notation we use with inverses, which is the f with the -1 here. So this means f inverse of x equals 7 minus x all over x. Okay, and so this thing that I'm boxing in red right here, that is our final answer for our formula here. And I apologize that at this point the work is a little sloppy. Hopefully you were able to follow it as we did it. All right, let's move right along. Just a reminder, when you're thinking about functions and whether or not they are invertible, meaning whether or not they have inverses, there's a test we can use to figure this out. And before I tell you what that test is, let's first maybe look at the ones here that are invertible. And I'll actually circle the ones that are. So this one down here, whoops. Oh, I just gave away the answer if you're paying attention. So this one right here is invertible. This one up here is, and so is this one here. So what do you notice about all of those? Well, if you read the last slide before I went away, what you probably noticed was they all passed the horizontal line test. Okay, so remember, a function is one-to-one, or it's invertible if and only if no horizontal line intersects its graph more than once. So if we can't draw a horizontal line that intersects the graph more than one time, then the function does have an inverse. So as an example of that, if we look at the first one up here, the y equals x squared, well, if I draw a horizontal line, oh boy, here we go. If I draw a horizontal line here, notice I can hit the graph in 2 spots. But on the y equals x cubed here, there's nowhere I can draw a horizontal line that will hit the graph more than one time. So that's what shows that this has an inverse. All right, and then the last thing for this video and this PowerPoint is we are talking about inverse trig functions here. So we ended section 1.1 and 1.2 talking about trig functions. We're going to do a similar thing here. So up at the top, you'll notice I've given you a list of the three, sorry about that, a list of the three inverse trig functions, or the three basic ones, and asked you to identify the domain and range of each. Now, I'm not going to go over that right now. I would suggest that you either look back to your notes from Math 142, or that you check in the textbook. Remember, there's a copy of the Precalculus textbook on WMAT to remind yourselves about those, because those are really useful for what we're going to do next. So use below, they tell us once we know the domain and range for each of these functions, to use that to find the values of these things here. So inverse sine of negative root 2 over 2, inverse cosine of negative 1, inverse tan of negative 1, and we're going to use find these using values on the unit circle. Now, for the first one, inverse sine of negative root 2 over 2. When you look up the domain and the range of this function, what you will hopefully recall or see is that it gives us answers in the first or fourth quadrant of our unit circle. So thinking about our unit circle here. Okay, inverse sine is going to give us answers here in the first or down here in the fourth. And also recall that it goes, its domain, or its range, excuse me, goes between negative pi over 2 and pi over 2. So any answers we get have to be in that range. So inverse sine of negative root 2 over 2. Well, the negative root 2 over 2, the sign being negative means we're in the fourth quadrant. I'm thinking about where in the fourth quadrant sine is equal to negative root 2 over 2. I know that that is true at 7 pi over 4. However, 7 pi over 4 is not between negative pi over 2 and pi over 2. So I use the coterminal angle negative pi over 4. Because that does fall into this range. So it's supposed to be a negative pi over 4. Let me see if I can write it a little bit better. That's a little better. Okay, so that's the answer for the first one. All right, inverse cosine of negative 1. So remember that cosine gives us answers in the first or the second quadrant. And here we have a negative, which means we're probably going to be in the second quadrant, so up here. And I also know that negative 1 is a unique value for cosine. That's actually one of the ones right along the axes. And that is going to occur at the value pi, is where inverse cosine is negative 1. All right, then inverse tan of negative 1. So we know that inverse tan gives us answers in the first or the fourth quadrant, just like inverse sine. Because it's negative, this means this, well, two ways to think about this. Either you just know that it's in the fourth quadrant, or tangent is sine over cosine. And if it's negative, that means the sine and the cosine both have different signs, like plus or minus signs on their values. And so that would have to be in the fourth quadrant as well, because in the first quadrant, both sine and cosine are positive. And they would also have to be the same because of this negative 1. So think about in the fourth quadrant where sine and cosine are the same. That's actually one we looked at already. That was at 7 pi over 4. Or again, because we have to be in that range of negative pi over 2 to pi over 2, we're talking about negative pi over 4 once more. So there are our answers. Okay. And that's it for right now. So if you have any questions about this, please feel free to reach out to me or catch me on a Zoom office hour class session. Hope you guys are all doing well. Talk to you soon.